Good evening, everyone. My name is Dennis Wong. This video is going to be a presentation for the assignment that I have done for MC18 Advanced MOSFET Technologies and Non-Ideal Effects. Basically, in this assignment, we have to simulate a FinFET transistor on online simulation tools, and in this case, we used the NanoHub simulation tool. The goal of this assignment is to investigate the characteristic or electronic properties of the FinFET device as the gate length of the FinFET is decreased. So we have properties such as the channel width, the thickness of the oxide, source, drain, length, etc. So those properties will remain the same throughout all the simulations that we will be doing. We will only change the gate length. So you can see here, device 1 is 60 nanometers, device 2 45, and device 3 30 nanometers. For this presentation, we'll be focusing on device 2 and 3 because previously we have already done device 1. So if we jump into the simulation results for the 45 nanometer transistor, if we look at the threshold voltage here, uh, we this is actually the ID to VG graph, and we plot the graph to get the threshold voltage. So keep this in mind. We will now compare this graph to the graph of the 30 nanometer FinFET. The difference here is not very obvious, but if we look closer, if we look at the y-axis, we compare the y-axis, we can tell that the curve for the 30 nanometer compared to the previous 40 nanometer, it moved upwards. So instead of very exponentially, it is less curved. So the gradient is less steep. So what does this mean? What is the significance of a lesser curved IDVG relationship, you might ask? For that, let us move on to the comparison table for all of the gate length for FinFET. If we look at, for example, the threshold voltage, we can tell that as we decrease the gate length, the threshold voltage of all of the FinFETs decrease progressively. And this is due to the fact that if we look at previously the IDVG graph, okay, we take the threshold voltage when the current is this value, right? So if the curve is less steep, we the phenomenon that we notice here is a shift to the left of the threshold voltage. And we this phenomenon is actually known as the short channel effect. So we notice that a trend whereby the gate length decreases, right? The IDVG curve is moving upwards. So there are several reasons to why this phenomenon is happening. But the main reason is because as we decrease the length of the gate, right, the the drain is able to penetrate even better into the channel. So the drain has more, the electric field of the drain is stronger, is able to penetrate into the channel compared to when the gate length is longer. Okay. So the consequences of that is we have lesser or weaker control of the transistor in this case. So if we look at for example, some of the parameters, the characteristics here, such as the subthreshold swing, we can see that as we decrease the channel gate length, right? The This is what the subthreshold swing is less and less steep. So if we recall the IDVG, the graph, right? The curve becomes less and less steep, right? So a less steep subthreshold swing means that the control of the on and off of the transistor is less sharp, or less sharp meaning the control, if the entire operation becomes more gradual. So as a result, the on and off states are less defined. And the consequences of that is uh, the system might not be that robust. There might be more errors, error prone, and it is not as accurate. So what are the some of the ways to get rid of this issue, or to make this issue lesser of a problem, is to increase is the whole point of a FinFET, to increase the number of the gates. So when we increase the gates, let's say we have a few gates uh, surrounding the transistor itself, we have more electrostatic control of the transistor, and then we can turn the transistor on and off. We can control the transistor better. So this is one of the ways to mitigate this issue, the short channel effect. And ideally, we would like to minimize the short channel effect, because it is one of the non-ideal effects in MOSFETs. Okay, so this concludes my very brief presentation for this topic. The conclusion here is that as we decrease the gate length of the MOSFET, we get a lot of non-ideal effects. And in this case, we get a weaker control of the transistor itself. Ideally, we want to mitigate that issue. One of the ways to do it is to add more gates. So thank you very much for watching this video. If you have any questions, I'll be very glad to try my best to answer them. Thank you.